And for the final video on redox, we're going to be looking at fuel cells. So just start off by showing you what a fuel cell looks like. We're just going to represent it as a box and really just break down the essential parts of a fuel cell. So first of all, you have to have a part of the box for the oxidizing agent or oxidant to enter. And this is oxygen gas. Then you have a side for the reducing agent to enter. And this can be many things. For example, you could have hydrogen gas, you could have a methanol fuel cell, you could have a methane fuel cell, and various other things. So something else you also have are the two electrodes. So we'll just put those in here. And you can just use basic chemical principles to understand this. So your anode is where oxidation will occur to your reducing agent. And your cathode is where reduction will occur of your oxidizing agent. And the charges of those, because we're getting electrical energy, is positive for the cathode and negative for the anode. So this is obtaining electrical energy. So the energy conversion is chemical to electrical, and we have spontaneous redox reactions. Other things are in between. You have an electrolyte. So your electrolyte will be here, and that'll allow the free movement of ions. Then you've got, so usually you need to know some properties of the electrodes. So the electrodes, remember, are the anode and the cathode. In fuel cells, they are generally catalytic. And they're also porous to gases. And they are also inert, so they don't participate in the redox reactions. The electrolyte is permeable to ions, so it allows ions to go through, but it's impermeable to gases and to electrons. So the electrons actually flow through an external circuit as shown, and the electrons, as we know, go from the reducing agent to the oxidizing agent spontaneously. The fuel cell reactions overall are pretty much like the combustion reaction of the fuel, but you can tell in the half equations whether it's in an acidic or basic environment. To connect to that with the electrochemical series, sorry that I don't have one with less writing on it, but you've got most of the fuel cell reactions here, well, definitely the ones for hydrogen oxygen fuel cell. So as you can see, you could have a hydrogen fuel cell where your fuel will be obviously hydrogen. You could have an acidic, or you could have an alkaline, and you need to be really quick at getting these half equations. So the one that's acidic, you have a look at for oxygen. Oxygen's present here and here, but as you can see, oxygen is further up in this half reaction. So this will actually occur spontaneously, preferentially. So this will be the reduction reaction for an acidic fuel cell. Acidic fuel cell the reduction of oxygen. And let's have a look at the hydrogen. Hydrogen's there. That's the acidic one. So these are the two for the acidic. I would just be really ready to write that out because they often just ask what is the reduction reaction for an acidic fuel cell. So acidic. Okay. And the half reduction equation, the reduction equations for the alkaline, well, you're looking for oxygen again, but you're looking for hydroxide. So that's this one here. So this will be alkaline or basic. And down here, you've got the hydrogen one. And if you do a quick calculation, you'll actually find that they both generate, under standard conditions, 1.23 volts. And also you will find that when you add them up, you actually get the same overall equation, which is oxygen gas plus hydrogen gas producing H2O. According to 25 degrees Celsius, it's liquid, but sometimes you'll see it being a gas. Just be wary of what the question's giving you. And then you balance by having two H's because you require 2 times the amount of H's to add up to 4 electrons as the oxygen half cell. So there you have it. Now, what other things do you have to watch out for? Well, what we're going to do is actually just go through some examples here. Okay, so here's our NEEP exam again. You can always pause it and do some questions by yourself, but let's have a look at how varying they are. So diagram below shows a simplified representation of a fuel cell. Reaction between methanol and oxygen. Nice, okay, that's fine. And it tells you here that methanol is gas in this case, so just be aware of that if it was a short answer. Also tells you what comes out. That makes sense because the overall should be like the combustion. In fact, I'll just write out the overall now. So methanol plus oxygen produces H2O, it's gas, plus CO2, and that is also gas. And then carbons are balanced, hydrogens are not balanced, so I need to pop a 2 there. And then 2 plus 2 is 4 oxygens, and you've only got 3 here, so I need to have 1.5 here. Okay, we'll just do it nice and quick like that. So the question's asking for the reaction occurring at the negative electrode. So the negative electrode's the anode, and we know that the anode is where oxidation occurs. So we're going to be looking for electrons on the right-hand side, which is representing oxidation. So let's just cross out the oxygen one. Everything else seems fine. Okay, now it is going to be oxidation of your fuel source. So can't be B and it can't be D. That's a really easy question if you break it down like that. But let's balance. I'll just show you it's the same as balancing for regular redox. It tells you that it's acidic because it tells you here. Have a look at your electrolyte. Your electrolyte has H+. So you balance using cohes. So first key element, yep, balanced. Then oxygen by adding water, H2O, yep. Then 4 H+, 3, 4, 5, 6 H+, yep, and 6 electrons. To double check, let's check the oxidation numbers. So that's +1, +1, +1 is +3, +1 is +4, -2 is +2, so it has to be -2. On the product side, you've got +4. Excellent. So we have lost, have you not? 6 electrons, exactly what we expect, so the answer must be A. Of course, you didn't have to go through all of that, but I'm trying to show you how to go in multiple ways. All right, fuel cells are not currently used widely used as an energy source. Let's discuss a few of the ways before we look at them. So fuel cells are quite expensive. They are a quiet energy source, which is good. Like they're more quiet than combustion. Hydrogen is pretty difficult to obtain. I'll actually show you the slide from the PowerPoint, and I actually want you to make sure you get this down. So a few of the things from the PowerPoint that you need to be aware of, and I'm not going to go through it because you can just look at it yourself. Actually comes out all right. So, oops. So first of all, they're thinking about switching to the hydrogen economy. Main reason, you know, obviously you get water as a byproduct, much better than carbon dioxide as well. But there are a few drawbacks of this. So first of all, producing hydrogen gas, it's actually produced using fossil fuels. So through steam reforming. 95% of it's actually produced that way. So it's very counterintuitive. You need to memorize this process of producing hydrogen gas through methane. So you need to memorize those 2 steps, write them out. And the other way we can do it is through the electrolysis of water. I'll quickly go into the electrolysis of water. So if you go back to your electrochemical series, you'll see that if we electrolyze water, so if we pass a current through water, the only things that could react, obviously, is water. So water is present both as an oxidant over here. So we write out that half equation. If you did electrolysis of water, I've seen them straight out ask for the half equations for electrolysis of water. So you need to know this. Electrolysis of water. So what would be occurring at reduction, which is the cathode, which is what polarity in electrolysis? That's right. So it'll be negative. Then you just copy it out straight from your electrochemical series. Plus 2 electrons produces H2 gas plus 2OH minus. Now, that's your half equation at your cathode. At your anode, you would have something positive, which is oxidation. And you've got water actually on your oxidation side, well, undergoing oxidation as a reductant. And you actually just write out straight from the electrochemical series. Okay, now if I were to add these 2 equations together, I would have to multiply the top equation by 2, and the bottom equation I would just keep as it is. So it would be 6H2O on this side, and crossing out electrons, 2H2, and I want to do it quickly. So that would be 4 hydroxides. Never actually do that to your half equations, but that would be 4 hydroxides and 4H plus. So that makes 4H2O and O2. All right. Then those waters cancel out and you get 2H2O on this side. And as you can see, we are producing H2 gas. So that's through the electrolysis of water. All right, you can get H2 gas. Now, we can do this in a green way because we can use renewable energy sources to provide us with the electrical energy to electrolyze water. Obviously, you can do this through non-renewable, but it's obviously better and greener to use renewable energy sources. And they get replenished as quickly as they are consumed, so they last longer. All right, well, indefinitely. Okay, let's go back to the questions. Got a bit sidetracked then. So, just zoom in. Okay. Fuel cells are not currently widely used. Which of the following factors is the least likely reason? Difficulties involved in storage and transportation of gaseous reactants. Well, let's have a look at our table of potential problems. All right, first of all, storing hydrogen gas. Hydrogen is it has a high energy content by mass, but it's a gas at room temperature, so we need to turn it into a liquid. This is actually very expensive. It takes a lot of energy to liquefy hydrogen. Also, this leads to needing larger fuel tanks. Compressed hydrogen, hydrogen also takes a lot of energy. You also need to have heavy maintenance on your hydrogen tank to make sure that there's no leaks. They've also got material-based storage of hydrogen, which is just coming out recently. There are safety issues, obviously, with hydrogen because it is flammable and can readily cause an explosion if it comes into contact with a spark. Also, because of its low density, it quickly disperses in a well-ventilated area, so that's a positive thing. You require strict codes and standards like maintenance detectors and maintenance of the canister and also hydrogen sensors to detect any leakages. Okay, so let's have a look. I would also look at this table in your own time. Okay, so difficulties involved in storage and transportation. That tends to be like a reason that we always look at, a potential problem. The very poor efficiency of energy conversion. Oh, the energy conversion of fuel cells is very high. Does it actually have it here? Yep. Higher energy efficiency than a coal-fired power station. So I would say that that's on the money for least likely. High cost of auxiliary systems needed to maintain. Yeah, we said it was a high cost. And also slow rate of reaction. Yeah. So in fuel cells, they all face that kind of slow rate of reaction. That's why the electrodes tend to be catalysts. So I would say that that is comfortably B. All right, moving on. Methanol can be used in fuel cells. Oh, how creative. They're using methanol again. The overall equation is this. Which of the following best describes the reaction occurring at the anode? So the anode is where oxidation occurs. This is a replica of the above question. So I would say it is anode is oxidation. Oh, using a potassium hydroxide. So now they're using a different electrolyte. They're using basic. This is actually really good. I would pause it here and practice writing out basic. So let's go through it. We have methanol on this side. We have CO2 on this side. So we'll start with cohes and then we'll add the hydroxide. Key element, balanced. Oxygen, add 1 water to this side. Hydrogen, we've got 4, 5, 6, so add 6 to this side. Now pause and add hydroxide. So we have to add 6 hydroxides to each side. Okay, and that's 6H2O. All right, that cancels with that, being 5H2O. Now, we have to also balance for charge. We have a -6 on the reactant side, so we need to add 6 electrons. Notice that the electrons are the same. So we actually have A for that. Okay, this is also part of this question. During the operation of the fuel cell, the pH of the solution near the cathode would. All right, the cathode is where reduction is occurring, and that's where the oxygen gas is being reduced. So what we would need to do for that is work out the half equation. which is actually on your electrochemical series. Let's take a sneaky look at it. This one's even less neat. All right, the hydroxide cathode reaction would be this one. So we're producing hydroxide. So concentration of hydroxide increases, meaning it's becoming more basic, which means that the pH would also increase. So let's have a look. Increase as hydroxide is produced, giving us option D. 2 questions left. Okay, fuel cells. Now we got methane. At least they're mixing it up a bit. Using an acidic electrolyte, note that. Write the half equations occurring at the anode. So the anode is where oxidation is occurring, and that is the fuel. Methane produces CO2, balanced through cohes. So 2H2O now, and 8H plus, and 8 electrons. At the cathode, look, you could do it in a sneaky way because you've got it here. So it's acidic and it's oxygen. So you can just copy it directly from your electrochemical series. May as well save time because the chem exam is very long. Okay, at which electrode, positive or negative, does oxygen react? Well, let's go through the thought process. Oxygen is reduced, which occurs at the cathode. We are dealing with the production of electrical energy, so it has to be positive. Okay, state 2 functions of the electrodes. You could say a number of things. 1, that they act as catalysts. 2, that they are porous to gases. What else could we say? What else would they accept in an exam? Which one are we doing? 0.11. Okay, we got all those right. Excellent. Positive. Okay, any one of these. The site of oxidation and reduction. There you go. If you're desperate, go for that one. Catalysts separate gaseous reactants, are porous to allow the passage of gases. So the gases actually enter the electrodes where they exchange electrons with it, either accepting or donating, but they can't get to each other so that the fuel and the oxygen do not spontaneously react. All right, final question. And I'm just going to zoom out so we can see the full question. Okay, an innovative way of using natural gas with a fuel cell is being developed by an Australian company. These cells use a ceramic electrolyte. Oh, I'm happy that they gave us this one. With natural gas, blah, blah, blah. Okay. The high voltages. All right, cool. Write the half equations. So now they're not telling you that it's in acidic or basic. They're telling you what the electrolyte is. You must balance with whatever electrolyte they're giving you. So let's have a look at the anode. The anode would be oxidation, which is of our fuel, which is methane. And it turns into CO2. Now, I can't balance with cohes because I've been given an electrolyte. So I must balance by adding oxide. And that's actually tough. I'm going to pause there and I'm going to do the overall equation first so that we can actually subtract the cathode one from the overall. Okay, I'll show you how to do that. So methane plus O2 produces CO2 and H2O. So we just balance for 2 there. All right, I'll do the cathode one first because it'll make the anode one easier. I just won't put states because it's in ceramic, which, that's the state. So oxygen produces oxide, and you've got 2 of these to balance with that, and you've got 4 electrons here to balance for charge. Now let's actually work on subtracting those two. Just get a clean piece of paper. All right, so your overall reaction is CH4 plus 2O2 produces CO2 plus H2H2O. Then you've got your cathode reaction, which is O2 plus 4 electrons produces 2O2 minus. Okay, now we need to have another half equation, which when it's added to this will equal that overall equation. So you have CH4 here. You also have CO2 there. You have 2H2O, which you don't have in your half equation, but you have in your overall. You've also got 2 oxygens. So you actually had to multiply that by 2. Okay, so keep that in mind. You needed to multiply that by 2. That means you need to have 4 oxides to balance with those 4 oxides coming out. And you might already be balanced. Let's double check. 4, 4, 4, and 4. Yep, you are balanced. And then adding electrons, add 8 electrons to that side. Now, let's just double check that we got that correct. And we have that. Perfect. And notice that they're not putting states. So VCAR wouldn't really expect states for this, but you could write in ceramic or something like that, but it's just really not necessary for that type of fuel cell. Write an equation for the overall. Oh, we've already done that. Let's just copy that out. That's fine. And do we get the same? Oh, I actually haven't put that answer in. That's nice. I will add those answers to it. Okay. Now, C. Natural gas. Let's have a look. Natural gas is also used for electricity generation in coal-fired power station. Which of these methods, fuel cell or gas-fired power station, produces the greater amount of electrical energy per mole of methane used? Explain your choice. All right, so you would actually get, it's a higher efficiency for the fuel cell. Okay, so because fuel cells only have one energy transformation as opposed to many energy transformations in a power station, like a natural gas power station, you would get energy losses in the fuel cell, at each stage of the natural gas natural gas power station that you wouldn't actually get in a fuel cell. So because of the higher efficiency, you would actually get more energy per mole of the fuel. So finally, D, the fuel cell produces an output of carbon dioxide, which is a greenhouse gas. Describe one way in which the fuel cell may be operated so that the overall contribution to this process is minimized. Okay, definitely you're going to go for biogas because you know that biogas is close to carbon neutral. So it's produced from the decomposition of organic matter. You'd call that biomass. And the carbon dioxide which enters the organic material is relatively equal to, well, it is equal to the carbon dioxide which is released during consumption of this fuel.